Today, we're delving into the paper D3RoMa Disparity Diffusion-based Depth Sensing for Material-Agnostic Robotic Manipulation. This research tackles a critical challenge in robotics: accurate depth sensing, particularly for challenging materials like transparent and specular surfaces. What are the core limitations of traditional depth sensing methods that D3RoMa aims to overcome?
Traditional methods, like those based on semi-global matching, SGM, or time-of-flight, TOF cameras, struggle with non-Lambertian surfaces, surfaces that don't reflect light uniformly. This includes transparent and specular objects where light paths are complex and lead to noisy, incomplete depth maps. These inaccuracies significantly hinder robot performance in manipulation tasks. Furthermore, occlusions and out-of-view areas prevent accurate correspondence estimation, a fundamental step in many stereo algorithms.
D3RoMa proposes a novel approach using a denoising diffusion probabilistic model. How does this differ from traditional learning-based methods for depth estimation? What are the key advantages of this approach?
Instead of relying on cost-volume construction and low-level feature matching, as in most prior works, D3RoMa frames depth estimation as an image-to-image translation problem. The diffusion model directly translates the left and right stereo images into a disparity map. This offers two main advantages. First, it allows for generative modeling of multimodal depth distributions, crucial for handling the ambiguity inherent in transparent and specular surfaces. Second, the iterative denoising process inherent in diffusion models replaces the iterative networks often used in previous approaches, simplifying the architecture.
The paper mentions integrating geometric constraints from traditional stereo vision. Can you elaborate on how this is achieved and the impact it has on the performance?
A left-right consistency constraint is incorporated as classifier guidance into the diffusion process. This is done by adding the gradient of a stereo matching loss function, based on photometric consistency and smoothness, to the score function of the diffusion model. This elegantly combines learning-based predictions with traditional geometric modeling, improving accuracy and robustness. The weighting between the learned and geometric gradients is a hyperparameter that can be tuned.
The success of any learning-based method hinges on the quality of the training data. The paper introduces a new synthetic dataset, HIS. What makes HIS unique, and how does it address the limitations of existing datasets?
HIS, Habitat Synthetic Scenes Dataset Isaacson Specular Transparent Diffuse, is a scene-level dataset simulating real, active stereo infrared patterns. It includes over 350 transparent and specular objects in over 160 indoor scenes, significantly expanding the diversity of existing datasets, which are often limited to tabletop settings or near diffusive materials. The realistic simulation of IR patterns and photorealistic renderings is key to its effectiveness in enabling real-world generalization. The two-pass rendering process ensures accurate depth even for transparent objects.
The paper presents extensive experimental results across several benchmarks. Can you highlight some of the key findings and how they demonstrate the superiority of D3RoMa?
D3RoMa achieves state-of-the-art performance on multiple public depth estimation benchmarks, including DREDS and Syntati, outperforming existing methods, especially in handling transparent and specular objects. The improvements are substantial, often exceeding 100% improvement in mean absolute error compared to baselines. Furthermore, real-world experiments demonstrate significant improvements in robotic manipulation tasks, such as grasping and mobile manipulation, showcasing the practical impact of accurate depth estimation. The results on the ClearPose dataset further highlight the robustness of D3RoMa in challenging real-world scenarios.
What are some of the limitations of D3RoMa and potential avenues for future research?
One limitation is the iterative inference process of the diffusion model, which can be computationally expensive. Future work could explore diffusion sampling acceleration techniques to address this. Another area for improvement is handling high-resolution images efficiently. Techniques like coarse-to-fine processing or patch-based processing could be investigated. Finally, exploring alternative guidance mechanisms beyond left-right consistency could further enhance performance.
The integration of geometric constraints within a diffusion model framework is a particularly interesting aspect. Have you considered exploring other types of geometric constraints or incorporating other modalities, such as RGB information, more directly into the diffusion process?
Absolutely. While left-right consistency is a strong geometric prior, other constraints, such as surface smoothness or normal consistency, could be incorporated. The framework is flexible enough to accommodate additional modalities. For instance, we experimented with incorporating color images from a third camera in active stereo settings, and while it provided a slight improvement, it wasn't a significant boost. More sophisticated fusion of RGB and depth information within the diffusion model is a promising area for future research. We also explored using raw disparity as an additional guidance signal, but found that the benefits were limited when the raw depth was noisy.
The paper emphasizes the importance of the HIS dataset. Could you elaborate on the process of creating this dataset and the specific choices made to ensure realism and diversity?
HIS leverages the high-quality indoor scenes from the Habitat Synthetic Scenes dataset, HSSD. We then populate these scenes with a diverse range of object models, including transparent and specular objects. The key to realism is the two-pass rendering process. The first pass renders the scene with diffuse materials to obtain accurate depth information. The second pass simulates the infrared patterns projected by a RealSense D415 camera, capturing the specific lighting effects on non-Lambertian surfaces. This ensures that the synthetic data accurately reflects the challenges of real-world depth sensing. Randomization of object materials, scene lighting, and object placement further enhances the dataset's diversity.
The experimental results show significant improvements in robotic manipulation tasks. Can you discuss the specific robotic setups used and the metrics employed to evaluate the performance?
We evaluated D3RoMa in 3 different robotic manipulation scenarios: tabletop grasping, articulated object manipulation, and mobile grasping. For tabletop grasping, we used a Franka Emika Panda robot arm. In mobile grasping, a custom-wheeled robot with a 7D-OF arm was employed. The success rate of grasping was the primary metric, with separate evaluations for specular, transparent, and diffusive objects. We compared D3RoMa against Dristines using the same motion planner but different depth sensing methods. The results consistently showed that D3RoMa significantly outperformed the baselines, demonstrating the practical benefits of improved depth perception.
The choice of using a diffusion model for depth estimation is interesting. Could you elaborate on the specific advantages of this approach compared to other generative models, such as GANs?
Diffusion models offer several advantages over GANs for this task. First, they are generally easier to train and less prone to mode collapse, a common issue in GANs. Second, the iterative denoising process naturally lends itself to refining the depth map, allowing for a more gradual and controlled improvement. Third, diffusion models provide a natural way to incorporate uncertainty estimation, which is valuable in robotics applications. While GANs can also generate high-quality images, their training instability and difficulty in controlling the generation process make them less suitable for the precise depth estimation required in robotic manipulation.
The paper mentions using a UNet architecture for the denoising network. What were the considerations behind this choice, and were any alternative architectures explored?
The UNet architecture was chosen for its effectiveness in image-to-image translation tasks and its ability to capture both local and global context. Its encoder-decoder structure allows for efficient processing of image features and accurate reconstruction of the disparity map. While other architectures could have been explored, the UNet's proven success in similar tasks made it a natural starting point. The experiments focused on optimizing the UNet's hyperparameters and exploring different loss functions rather than investigating alternative architectures.
The integration of the left-right consistency loss is a key component of D3RoMa. Could you discuss the specific form of this loss and how it's incorporated into the diffusion model's training process?
The left-right consistency loss is based on comparing the left image with a warped version of the right image using the estimated disparity to perform the warping. We used a combination of structural similarity index, SM, and an edge-aware smoothness loss. The gradient of this loss function is then added to the score function of the diffusion model during the reverse sampling process. The weighting factor S controls the balance between the learned gradient from the diffusion model and the geometric gradient from the stereo matching. This allows for a flexible control over the influence of the geometric prior.
The paper highlights the importance of data diversity for generalization. How does the HIS dataset contribute to this, and what strategies were employed to ensure the dataset's robustness and generalizability?
The HIS dataset's contribution to generalization stems from its scene-level diversity and the inclusion of a wide range of object types and materials. The use of 168 different indoor scenes from HSSD, combined with over 350 object models, ensures a broad representation of real-world environments. The randomization of object materials, scene lighting, and object placement further enhances the dataset's robustness. The two-pass rendering process, as mentioned earlier, is crucial for accurately capturing the depth of transparent objects. This combination of factors ensures that the model trained on HIS is less likely to overfit to specific scene characteristics and can generalize well to unseen scenarios.
The paper mentions using a cosine scheduler for the diffusion process. What were the reasons for this choice, and how does it compare to other scheduling strategies?
The cosine scheduler was chosen for its effectiveness in controlling the variance of the noise during the diffusion process. It provides a smooth and gradual decrease in noise, allowing for a more stable and controlled denoising process. Other scheduling strategies, such as linear scheduling, were explored, but the cosine scheduler yielded better results in our experiments. The choice of scheduler is a hyperparameter that can be tuned, and the optimal choice may depend on the specific dataset and network architecture.
The ablation studies in the paper provide valuable insights into the different components of 3RoMa. Can you summarize the key findings from these studies?
The ablation studies confirm the importance of each component of 3RoMa. Conditioning on both the left and right images, as well as the raw disparity map, significantly improved performance. The integration of the geometric guidance further enhanced accuracy, particularly in challenging real-world scenarios. Experiments with different network architectures, loss functions, and noise strategies showed that the chosen configurations were optimal. These studies demonstrate the synergistic effect of combining the diffusion model with geometric constraints and the importance of a well-designed training dataset.
The paper demonstrates the effectiveness of 3RoMa in various robotic manipulation tasks. Could you elaborate on the challenges involved in transferring the model from simulation to the real world and the strategies employed to mitigate the sim-to-real gap?
The sim-to-real gap is a significant challenge in robotics. Differences in lighting, object textures, and sensor noise between simulated and real environments can lead to performance degradation. The use of a large, diverse, and realistic synthetic dataset like HIS is crucial in mitigating this gap. By simulating real-world conditions as accurately as possible, the model trained on HIS is better prepared to handle the complexities of real-world scenarios. Furthermore, the integration of geometric constraints helps to improve the model's robustness to noise and variations in real-world data.
The paper mentions using GSNet for grasping cause prediction. Could you elaborate on the role of GSNet in the overall pipeline and how it interacts with 3RoMa's depth estimation?
GSNet is a separate module responsible for predicting 6D OF grasping poses given a point cloud. 3RoMa provides the high-quality depth map, which is then converted into a point cloud. This point cloud serves as input to GSNet, which predicts the optimal grasping pose. The integration of 3RoMa and GSNet forms a complete pipeline for robotic grasping, where 3RoMa provides accurate depth perception and GSNet leverages this information to plan successful grasps.
The paper focuses on depth estimation for stereo images. Could the proposed method be extended to monocular depth estimation? What modifications would be necessary?
While the current implementation is tailored for stereo images, extending it to monocular depth estimation is a potential area for future research. The key challenge would be adapting the geometric constraints, as monocular depth estimation lacks the direct correspondence information available in stereo images. Alternative geometric priors, such as surface smoothness or normal consistency, could be explored. Furthermore, the training process would need to be modified to account for the lack of stereo information. However, the core diffusion model framework could potentially be adapted to handle monocular inputs.
The paper mentions several metrics for evaluating depth estimation performance. Could you discuss the rationale behind choosing these specific metrics and their relative importance in the context of robotic manipulation?
The choice of metrics reflects the different aspects of depth estimation relevant to robotic manipulation. RMSE, root mean squared error, and MEI, mean absolute error, measure the overall accuracy of the depth map. REL, relative depth error, focuses on the relative accuracy, which is important for tasks where the absolute scale is less critical. The accuracy metrics provide a more nuanced assessment of accuracy at different tolerance levels. These metrics, taken together, provide a comprehensive evaluation of the depth map's quality and its suitability for robotic manipulation tasks. The choice of metrics is also influenced by the specific datasets used for evaluation, as different datasets may have different characteristics and noise levels.
This has been a very insightful discussion on 3RoMa. Thank you for your expertise.